Hello, thanks for joining me in this video where I am going to talk about electrocyclic reactions. So in electrocyclic reactions, what we know is that we transform one pi bond. So like here we can transform this into a sigma bond. So we create a new sigma bond here. And that pi bond moves position, that moves position. So one of the pi bonds is converted into a sigma bond. So we create a new sigma bond. So here we can assume this is the new sigma bond, this one here. Okay. When we do electrocyclic reactions, the main thing is, if you look at any of these kind of reactions in the scheme, how can we be able to predict the outcome with the correct stereochemistry? So if we start from here, how can we make sure that we can predict the correct stereochemistry? Or if we start from here, how can we be able to predict the correct stereochemistry of the product? Okay? Now, that is what we need to achieve by the end of this video. You cannot memorize any of this. If you do, you're going to get more confused and it will not work for you. Okay? Now, let us see what we could do. What we need to do is to understand the frontier orbitals. We can consider the 1,3,5 hexatriene, that is 6p orbitals. So we need to identify the HOMO and the LUMO. Because we have 6 electrons, all we need to do is think of, at the ground state, how many nodes are going to be in the HOMO. Obviously for 6 electrons, because each of the orbitals is going to have 2 electrons, so it's going to be side 3 is going to be the HOMO. Okay, so if we use our shorthand, our side 3 is going to be here, the HOMO with 2 electrons at ground state. Okay, then we move to the excited state. In the excited state, that means we are using light. When we use light, HOMO is redefined. So when we do the reaction by using heat, then we consider the HOMO to be the actual one. When we do the reaction in the presence of light, we consider the HOMO to be the former LUMO, because we have excited an electron from the HOMO to the former LUMO, and now we have a new HOMO. In every given case, you need to identify the correct HOMO. Okay? Let us look at this reaction, assuming we want to predict the outcome, which is this product here, when we use heat. How do we achieve that? Okay? What I want you to do is, we need to identify how many atoms are involved in the transition state. Of course, here there are only 6 atoms, because this is going to move here to form that sigma bond, which triggers that one to move there, and that one moves there. So we are doing it using heat, so there is no light, so we are not doing any excitation of an electron. So the HOMO is going to be side 3. Side 3 has 2 nodes. Okay, that's all we need to know. We don't have to draw all those side 1, 2, 3. We just need to know how many nodes are there, and then we draw the correct HOMO. Once you draw it, we are going to consider only the first one and the last one. So I want you to look at this structure and let us rotate it 90 degrees clockwise, and we are going to get this stuff here, 90 degrees clockwise. So this one, the methyl group, is that one, and this other methyl group, the one on the left, is this one. Okay, so we are going to consider, let us assume this is the number 1 and this is number 6. Okay, so 1, 2, 3, 4, 5, 6. We are only going to look at number 1 and number 6. Okay, so what you do is you use number 1 and number 6. Make sure that you have the correct shadings. The reds are the ones that are down, so I'm shading that. The blue in this case is going to be unshaded. Then don't really care about 2, 3, 4, and 5. Just draw a curve like that. And then we have CH3 here, the hydrogen here, and that methyl group over there. So what you see is just this one. So what I want you to do is just move from here directly to this position. Once you use the first and the last, and you have them aligned properly like the way you've done, what we want to do is to make sure that we do a rotation so that we can either have the reds meeting together or we can have the blues. So if you want to have the reds, it does not matter whether you do the blue or the red. If they are going to be cis, they're going to be cis. If they're going to be trans, they're going to be trans. Okay? So if we do it that way, this is going to be counterclockwise and this is going to be clockwise. So if we have different kinds of directions or rotations so that we can have them meet together, we say that is disrotatory. Now, when you rotate this one here, to make sure they meet, it means you're rotating this by 90 degrees. So when you rotate it by 90 degrees, this one also moves by 90 degrees. So it's going to move from here to where this other one was. So you end up with the CH3 being here. And when you rotate this one also kind of 90 degrees so that they align horizontally, this is also going to move in the same direction and it's going to be over there. So all of the methyl groups are going to be on the same side, so cis. So you form the cis product. Okay? You can do this with any reaction that involves heat, and you take the first, the last, make sure you have the right drawing. If one of the CH3 was on the inside, you're going to do the same, okay? And you end up with the product. So I want you to practice with the other reactions on the scheme, and let's see what you get. Next, I want us to look at a photochemical reaction. In this case, let us use one that involves 4 pi electrons. So starting from this one here, let us try to predict the outcome of that reaction. So we are going to do the same. You need to identify the HOMO, and we need to identify the LUMO. But now we are using light, so our HOMO is going to be the one where an electron has been excited. So because there are 4 carbon atoms, the HOMO is supposed to be psi 2. Okay? So that means we utilize 4 electrons. But with light, the HOMO is going to be psi 3 after we excite 1 electron. So we need to draw the HOMO for psi 3, the excited state. Psi 3 is going to have 2 nodes. So we start with the ground state HOMO, excite an electron, then we get the excited HOMO. Excited HOMO is the one we use. So we take the first and the last, and we do exactly the same thing. The first, so blue, the last, blue. Okay, see they're aligned properly. We don't care about anything in the middle. So remember what I said is you flip this one, like rotate it 90 degrees, and you get exactly what we have here. And what you need to do is, this CH3 is towards the outside. In this case, this other CH3 is also towards the outside. So when we do the rotation, this rotatory, we end up with this compound. All right? Let us do just one more. Let us try another one involving, assuming we used heat. Okay, so assuming we went in this direction. So from here to that. If we used heat, then this is what's going to happen. We are going to use the HOMO in the ground state. So we are going to have the first one is, we have the blue at the top, so the red here at the bottom. And the last one we have the blue at the bottom, so red is at the top. And all you need to draw is a curve like that. And the CH3 is towards the outside, and this is also towards the outside, and there's a hydrogen here, and then we want to make sure that we have the right kind of rotation. So if you want the reds to meet, we have to rotate this one 90 degrees counterclockwise. This one we rotate it also counterclockwise 90 degrees because we want the reds to meet. So counterclockwise 90 degrees. So when you rotate this 90 degrees, the CH3, you're going to have something like this. You're going to have the reds like that. That's going to be the red. And then you have the blue, which in this case is the unshaded, and that. And our CH3 here is going to be down. And the other CH3 is going to be up. Hydrogen, hydrogen. All right, you have a good one.